believe you requested some assistance recovering a lost ring.
Oh, yes. It was a gift from my late husband.
How precious. Can you describe it for me?
Yes, it was large with three. Actually, I have a photo. Here. This is on our wedding day.
Can I keep this?
Please. But be sure to return it after. It's the only print.
I shall do my best.
Thank you. Feel free to search the house if the thief has left a trail.
Thank you. This opens. Interesting.
By God, this isn't the Duchess. But she's wearing the same ring. I'll have to look into this.
Physical light is an electromagnetic wave and, unlike other forms of energy, does not need a material medium for transmission. We can see this from the way that light travels from the sun to the earth through the vacuum of space. A French scientist, Jean Foucault, found that light travels in water at approximately 3/4 of the speed as it does in air. Other matter mediums, interestingly, produce different values, but the speed is always slower than in a vacuum.
Notice how a straight stick appears bent when partially immersed in water? This effect is caused by the refraction or change in direction of light as it passes at an angle from one medium to the other.
Good day, Sherlock. How are you coming along?
Very well, thank you. But I was wondering if you have any other information concerning the ring.
My husband purchased it at his jeweler's. One of a kind. Very expensive, I'm sure. Is that all you need? I do have the specifications
No.
somewhere.
That's all I need. Light slows down when it travels from a vacuum into any other medium. The medium in which light travels through more slowly is called a refractive medium. For example, diamond is a more refractive and optically dense medium than glass, since light travels more slowly in it than in glass. You can notice how in the more optically dense medium, the refractive rate bends towards the normal. Because light travels in a relatively similar speed in air as in a vacuum, c can also represent the speed of light in air. It's only in extreme cases that the difference in speed in air and vacuum is noted. It's just as I predicted. The poor Duchess.
In developing a general equation for the refraction of light, we can replace the variables with these. Thus, the expression is written as sine 1 over sine 2 is equal to n2 over n1, or n1 times sine theta 1 is n2 times sine theta 2.
For instance, the value of an air-glass interface is about 1.5. See here, the angle of incidence is 30 degrees, and the angle of refraction is 19 degrees. So using the equation, sine 30 over sine 19 is the constant, which is approximately equal to 1.5. Doesn't this look strikingly like the index of refraction for glass? Referring to a chart, we can see that the n value for glass is approximately 1.54. Thus, the constant derived from the ratio is actually the index of refraction.
The diamond is famous for its sparkle because the light coming from it glitters as the diamond is moved about. Why does a diamond exhibit such brilliance? The answer lies in the diamond's high index of refraction. The high index of refraction results in a low critical angle of only 24.42 degrees. Compare this to glass, with a critical angle of 41.48 degrees. When the angle of incidence exceeds the critical angle, there is no refracted light. All of the incident light is reflected back into the medium. A cut diamond is designed to maximize the total internal reflection inside the diamond, which gives the diamond its glittery qualities.
Duchess, I have some distressing news for you.
Suppose the ring's still missing then.
No, as a matter of fact, it's right here.
Oh, thank you!
I had it made this morning.
What?
It's a copy. A second copy, in fact.
Second copy?
I'm sorry.
But my ring is one of a kind.
That's what got me onto it. Take a look at these.
This woman, she's wearing the same ring.
Indeed. The real one, if I'm not mistaken.
But how?
The one you lost was fake. Look closer. It doesn't sparkle as much as the other one. Your ring was made of glass. The real one is of diamond, and it rests for now on a